Kenyan for inviting and being a very nice host. So I'll say something about formal orbifolds. So I'll define these objects and ramification theory. So this main motivation of defining this was to study wild ramification in some reasonable way. So the story started with dimension 1. So maybe I'll start with dimension 1 and then go on. So let X be a normal variety over so initially it was algebraically closed field. So when we were the first project started, but it works over more general field and over a perfect field, slightly more general field, perfect field K. And so normal in dimension. So if dimension X is 1, then it's automatically regular. So it's much stronger. But in general, normal doesn't imply non-singular. So it's slightly general. But normal is the least we need to make sense of things. So normally I'll think of K as a field of positive characteristic. Characteristic K equals P is greater than 0. Though some of it will work in most of it will work in characteristic 0, but may not be as interesting, so to speak. Yeah. So the reason is the motivating reason to define this formal orbifold, as I said, is to study ramification theory. So maybe I'll start with what happens in characteristic 0 slightly, and then quickly shift to this thing. So let phi be a cover I finite separable dominant morphism. So separable basically means generically ital and should be dominant, and and I assume Y is again normal. Y normal. Okay, and so in case of dimension 1, this phi is ramified at finitely many points. And one can so say x little x in X is say ramified, then one can understand how the local picture or maybe I should say little y in Y is ramified and X is its image, which is a branch point, is ramified, and say phi y is equal to X is any element of X. Then what happens locally? So if characteristic K is 0, then this extension O y y, this local extension, maybe to really get rid of the global data, one should sort of complete it so that one y yeah at xx. So this extension is determined by the degree of by the ramification index. Yeah. So this extension, K is maybe forget. K algebraically closed, so maybe we can also say K is C. Yeah, so this extension is essentially determined by the ramification index. Yeah, so so it's going to be at the level of function field, it's going to be a cyclic extension of degree, same as the degree of this thing. Yeah, but in characteristic P, but if characteristic of K is equal to P, then the degree of this extension won't determine this the corresponding field extension, right? Because of the Artin-Schreier, various Artin-Schreier extensions, right? So for example, if we have x to P1 branched at infinity at say so maybe the local coordinate here is x, then branched at x equals infinity. So say this is a basically, so say this is an Artin-Schreier cover, i.e. it's given, so at the level of function field, this is given by, so function field is kx, function field of P1, and at the level of function field the extension is given by join z and go mod z power p minus z minus some polynomial fx. So this is the function field of capital X, and yeah, so this so this is going to give you a p-cyclic extension, which is so fx is, I should say where fx is in this polynomial ring kx. Yeah, so so it's clear it is straightforward to see that this is an Ital cover and it's ramified only at infinity, and depending upon which polynomial you take, it will give you a different field extension. So locally at so maybe I should just complete this picture. So locally this OP1 x comma infinity hat basically is k round square bracket x inverse. Yeah, local coordinate at infinity, I can think of it as x inverse, and then this actually is going to be totally ramified at x equals infinity. So there is actually a unique point there. Which will again denoted by infinity, since there is only one point. Let's not worry about it. So this is so maybe I'll look at it. So this is going to be given by so I'll join z. So maybe it's one should pass to the normalization if this is not normal, but if it is normal, it's okay. So maybe I'll just put a tilde. Yeah, so one should pass through the normalization. So I was thinking of writing it in terms of function field, and then it doesn't matter, but ideally one should pass through the normalization. So depending upon what the degree of R is, this extension can change, for instance. But even if you fix the degree of R, this extension varies depending. So I mean, if you take two different polynomials, it will give you, most likely it will give you different extensions most of the time. Very rarely, I mean, there is a precise condition. The Artin-Schreier theory tells you the precise condition when the two extensions are same. So this is the reason that one shouldn't just expect degree of the extension to recover the local data of a cover. Yeah, so one should have more. One should put in more information, or put in a data which contains more information to study these ramification problems. Okay, so that is the main motivation to define branch data. So definition.
Okay, so
So branch data P on X. So so what it does is, so again I still am at the moment I'm thinking of dimension 1. So what it does is is an assignment which assigns Galois extension Px of Kxx for x in X, a closed point. So a finite Galois, I should write a finite Galois extension.
Kxx is the completion.
Yeah. The fraction field of the completion of the, yeah, closed point of X, and where maybe I just write it down, where Kxx is the fraction field of Oxx hat. So one can do this theory with instead of completion you can pass to initialization as well. It doesn't change much. I mean, if you prefer remaining in the algebraic extension category, but doesn't matter. Artin's algebraization theorem tells you, approximation theorem tells you that they are the same thing more or less. Yeah, theory is parallel. So is an assignment like this such that so we want further condition. So I mean, as you see, the motivating reason is to look at this example, for instance. Yeah, so this will have branched. This will be branched only at finitely many points. So you want this to be more or less trivial extension if at most points, only at finitely many points you want this to be non-trivial extension. Yeah, so such that branch locus of P, which is defined to be x in X, close point, such that Px over Kxx is ramified. So this is the definition of branch locus of P, is closed, is a proper closed subset of X. Closed subset of X. So it should be at least codimension 1. So if I mean, if one could let X to be disconnected, I mean possibly disconnected, then one should say it should be at least codimension 1. Okay. So a formal orbifold is just a sphere. Formal orbifold is a pair x comma p, where x is a normal variety and p is a branch locus, branch data on X. Okay. So now maybe I'll just modify in higher dimension what happens. So how to modify the branch data in higher dimension. So that this makes sense more generally. Yeah. So in higher dimension, maybe first maybe one example, yeah, of branch data. So f from y to x is a cover, is a Galois cover, let's say. Then one can associate a branch data on x from this cover, right? So the obvious thing to do is, so I'll denote this branch data is usually I denote it by this thing. BFX is just O or rather fraction field of OYY hat, where y in y is a point above x. This is going to be, first of all, since this is a Galois cover, it doesn't depend upon which y you choose above x. It's going to be the same extension, field extension, and in this group also, as a subgroup of the Galois group, will be different, but they are all conjugates, so they are going to be isomorphic. Okay. So this though it looks like it's defined in terms of y, it's sort of independent of the choice of y.
Do you allow this P of x to be just the same as K x x?
Yeah. So
empty set?
yeah. So O. So that has a notation. So a trivial branch data, the trivial branch data on x, trivial branch data on x, O is Ox is same as Kxx. Yeah. So of course then the branch locus is empty. Here the branch locus is precisely the branch locus of f. Yeah, and yeah.
But is it obvious that we have always something non-trivial?
Yeah. So if you take a branched cover, then of course.
Take any cover.
Yeah. You can take any cover, then it will obviously be non. If it is ramified cover, then it will.
Right.
If it is etal cover, then this extensions need not be trivial, but branch locus will be trivial because it's etal by definition.
Okay.
Yeah. So this is sort of example in which sort of works even in higher dimension. But let me just say what I. So the definition you just have to. So in higher dimension, one has to look at first of all, there may be points of different codimension, and then completion one has to take some affine open subset, because the completion sort of depends upon which affine neighborhood you take. Yeah. So you just modify. So in higher dimension, for x in x of codimension at least 1, and u an affine open neighborhood of x, one takes one defines pxu to be so the assignment is this should be a finite Galois extension of a kxu, which is the fraction field. So maybe I'll just write it this way, which is the fraction field of. So you look at OXU. This is a this is a ring, and you complete it at the point at the prime ideal corresponding to that point. Yeah. And then you enforce some insist that it satisfies some compatibility conditions. So maybe I'll just write down. So yeah, so satisfying so for some compatibility conditions, one of them is, so if X is contained in V, is contained in U, contained in X, so these are both a fine open neighborhood of X, then PXV should be equal to PXU KXXB. Okay. So what happens is this field actually contains KXXU. Okay, so it makes sense. So you are further localizing and then completing. So of course it contains. Yeah. So and second is if X1 is a point contained in, say, the closure of some other point X2. Yeah. Then again you want that Px1 U should be equal to Px2 U Kx1 of U. Okay. So again Kx2 of U is actually contained in Kx1 of U. Okay. So just looking at completions, you get this thing. Okay, so now what is a morphism of form? So once we have so this is sort of general extending this definition to this thing, and then you again want this branch locus. So one can again define. So it's not difficult. So one defines Px to be just I don't know, Pxu Kxx, where Kxx is the fraction field of is the same thing what it is here. Yeah. But now the point is need not be closed points. Okay. And this does not depend upon the choice of U. Okay. So you take a smaller one, then they all, so it's independent of the choice of U, and then you can define the branch locus similarly. So you insist that this BLP, so this third condition is that BLP, which is defined in the same way, is of codimension at least one, is closed of codimension, closed in X of codimension at least one. Okay, so this is the branch data in higher dimension. So now one can define more.
So we suppose that X is normal. Is it just to guarantee that these regular? What's the purpose of normality we supposed? In the curve case, I can see that. But,
yeah. So I mean, when we sort of so there are many advantages of normality. Okay. First of all, anyway, when I want to take the cover, so it becomes, first of all, we are just studying fields in some sense, because we take the normalization and stuff, and then there are some other. So when you take the normal, so for instance, if you take normal, then you can't get curves like varieties which cross each other. Okay. So if it is normal, then then either you will have so if it is, it can't, the irreducible component will be disjoint, so it makes study better that way as well. And secondly, it has depth too, so that is also very useful in various things. and Henselnization, etc., is also at many places it turned out to be useful. I mean, I started off normalization because that's what I wanted to study, but then I realized it's useful at various places. Yeah. So okay. So a morphism. So unfortunately, that too many definition. Morphism of formal orbifold is from x, so maybe yq to xp is as a dominant separable admissible. So in the paper I've called it admissible morphism. So certain morphisms which I want to allow is a dominant separable quasi-finite morphism f from y to x such that this qy for any point, any codimension at least one point y, qy should contain p of fy. Okay. So qy is a Galois extension of kyy. It should contain p of fy, and we say that this morphism is ital if it is a equality here. Okay, and it is. So this should be true for all y in y of this kind of codimension greater equal 1, and f is called ital. F is ital at y if qy equals p of y, and it is ital if this holds everywhere. So so unfortunately, one of the problem in this thing is that even if this is a ital morphism of formal orbifolds, so away from the branch locus of p, this is going to be ital, right, on the nose, because the problem only occurs. But and in particular flat over that. But if you take a point in branch locus of p, then the morphism need not be flat over it. So that is one of the difficulty in sort of working with the setup. But nevertheless, we'll get to. I'll point out where this is sort of issue. One of
the. Do you allow x to be actually non-integral? I mean, you can like several components.
Yeah, but but the connected components are going to be integral, right? Okay. So that is. So in some sense, the generalization is not too complicated, yeah, because it's normal, right?
So like y could be the disjoint union of these.
Yeah, exactly.
Okay.
Yeah. And if f happens to be finite as well, then we call it a cover again. Yeah, right now it is allowed to be quasi-finite. Okay. So the good thing is that if you take some properties is that base change of ital morphisms base change or composition, and maybe I'll just put here composition of ital morphisms are ital. So in particular, it tells you that the fiber product of two ital morphism is going to be ital.
When you say base change
with
in the usual sense or in this morphism?
In this setup, yeah. So I should also tell you what the fiber product is. So I plan to tell you so roughly what the fiber product is. So I mean, so you have say two maps. Okay, I should have left some space above, but it's okay. Maybe we'll do a fiber product in a non-traditional way. Okay. So we want the fiber product in this category. So in the usual category, the fiber product is the usual fiber product. But since we want to be in the formal orbifold category, this is not necessarily normal. So you have to pass to the normalization. So, but this again satisfies the normalization is also a universal property kind of thing. And then you put you have to cook up a branch data here. So which is also, so I won't get into detail, but what you do is, so point is, if you have x to y maybe y to x some finite quasi-finite dominant separable morphism, and you have a branch data here, say p, okay, then you can cook up f upper star p, which will be a branch data on y, some natural thing, which is which you can guess what it is. So f upper star p of y should be, so in curve case this is f upper star of p of y will be basically p of f of, so let's say this is f, p of f of y times k y y. Okay, so this is what pullback of this branch data is. So A is basic. So in higher dimension, this is slightly more complicated, but not the same idea works. So what you do is you pull back. So you pull back Q. So you have a map from normalized fiber product to Y2. You pull back Q2 here. So let's call this map P1 and this P2. So you take P1 upper star Q1 and P2 upper star Q2, and you can define the compositum of two branch data. So this is just the compositum of these. A is basically compositum of these two branch data. So this is the fiber product, and in this sense, it should be ital, yeah, fiber product of two things. So once you have this, then one can show that this. Then one can define the ital fundamental group. So you have an inverse system. So you can define an ital fundamental group of these things, because fiber product of two ital remains ital, and so on. So you can, given any two covers, you can dominate by a bigger cover, so to speak. So
I have a stupid question. Do you possibly have some kind of like a proper push forward analog kind of things here?
Proper push forward of
kind of whole structure. Maybe it's difficult, but
for bundles we have some vector bundles on XP.
Yeah. For instance, if you have two things, then can I have like an intersection of the field or something like that?
Oh yeah, so that works out in curve case, but it doesn't. I mean, it so intersection of if you take in curve case, I think it is a branch data, but in higher dimension the intersection wouldn't be a branch data. It doesn't quite make sense.
Like sub-bundles of vector bundle is not necessary.
Yeah, exactly. Some compatibility doesn't match up.
Okay. So there is no push forward of structure.
Yeah, you can't push forward a branch data downstairs in some sense. Yeah, but and anyway, I couldn't find a reasonable geometric meaning of the intersection in some sense. So. But yeah, so that also reminds me, I should say, so in dimension x, this is dimension x equals 1. This is these things were studied jointly with it is joint work with A.J. Parmeshwaran, who is a TIFR. Yeah, so what I was going to say is that this allows us to So first of all, fiber product of etal is etal. So one gets that. So one can define pi 1 of x comma p, where p is any. So x comma p is a formal orbifold. Yeah. So can define. Yeah. So I should have. Okay. So now the good thing is this pi 1 of x comma p actually approximates pi 1 of so maybe I'll write it as a theorem maybe. So x a normal variety u contained in X open, then one can look at pi 1 of u. So so this can be approximated using pi 1 of x comma p, where p varies. P is a branch data on X such that the branch locus of P intersection U is empty. Yeah, so it is contained in the complement. So this is not too difficult to show once you know that how the setup is. Yeah. So so in some sense this you can approximate by these guys. And so one observation about this is that if X is proper, is also proper, so above hypothesis plus proper, then pi 1 of xp is of finite rank as a profinite group. So note that these groups are not of finite rank as a profinite group. Is the number of generators is sort of topological generators is infinite even for the curve case, and hence for other cases. But when x is proper, then pi 1 of x is finitely generated profinite group, and same holds in this case. So in some sense we are approximating this guy with this, but of course you have to take a lot of branch data. So I mean there is no contradiction as such, but just saying that one can try to study this by these things which are slightly well behaved. Yeah. So okay. So one thing which I studied about in the setup in slightly more detail was what is called is a variant of Lefschetz theorem for fundamental group, or these days called Grothendieck-Lefschetz theorem. So maybe I'll first start with what is this Lefschetz theorem for fundamental group. So this classical one is actually due to Lefschetz himself. Theorem for fundamental group. Okay. So what does that say? So let X be a smooth complex quasi-projective variety, and Y contained in X be a hypersurface. So maybe I should say not then. So it need not be true for all Y, but most wise it works. Then there exists y containing x a hypersurface so we are assuming quasi-projective, so it makes sense, yeah, of x such that the map pi 1 y, so the induced, so we'll have a map from pi 1 y to pi 1 x. This natural map is so this is surjective if dimension x is greater or equal to, and is an isomorphism if dimension x is greater or equal to 3. Yeah, so this is the classical version of Lester's theorem. So so this version was extended by Grothendieck in a slightly more general setup. So maybe this one should attribute to Grothendieck. So maybe instead of rewriting this, I'll say in what cases this is true. So true for arbitrary, so I mean arbitrary field of characteristic 0. So I think even this part is sort of due to Grothendieck. The machinery gave his machinery gave it for arbitrary field. X. If you take x projectives, so many things are there. So I mean, his goal was not just to do characteristic 0 as usual. He wants to do something. So if x is projective, and then this is true for characteristic p field as well. Characteristic p greater than 0 as well. Characteristic k, I should say, greater than 0. So arbitrary field. But for quasi-projective is not is actually false, but for some reasons I'll come to that. But for x quasi-projective, if you only look at prime to p part of the fundamental group, then this is okay. Yeah, so pi 1 p prime y to pi 1 p prime x, the same statement works out. Yeah, so if you look at the prime to p part of the fundamental group, then this is indeed surjective if dimension x is equal to 2. That means fundamental group of a general curve. So in fact this is true. I mean, it's not like some abstract y you have to take. Most of the y works, and yeah. So one can actually strengthen this to the tame case by following more or less the same route, and this is there is a tame version which is surprisingly recent. So maybe this is due to Eno and her one of her student last winter. So they realized that this is missing, so they show that it is true for you. This replace this by tame fundamental group. Okay. So they show that even for tame fundamental group this works. Okay, so this is maybe 2012 or something. Yeah, so but if you want to do the full thing, then it's actually false. So in general it is false in general, and the reason is that too many wildly ramified covers. So the point is, given any hypersurface, you can find some wildly ramified cover such that when you pull back it will get it will remain étale, but it will be some disconnected étale or something, which sort of is a a hindrance to become for this surjectivity, for instance. Yeah. So it is false in general, even, so maybe I'll say even when something like x equals e2. So if there is room for ramification, then it will fail. And y is, so no matter which which curve you take, you can always find a cover of A2, which when you pull back to y will be a disconnected. You start with a connected cover and pull back to y, it will become disconnected. So that is in some sense won't work out.
Does it have anything to do with imperfect survey field, or maybe just?
No, it doesn't. Even over algebraically closed field, this won't work. It's more to do with existence of wildly ramified covers. Okay. So the curve will be defined by some equation. You take a complicated enough equation, then it won't work.
It's not an arithmetic thing.
No, it's not. It's a geometric problem. Okay. So the framework, one has to define a framework properly. So I think this is the framework where. So before I get to how to attack this problem in this framework, because what I do is basically carry out Grothendieck's algorithm to attack this. Yeah. So what is broadly Grothendieck's proof? So proof is that he looks at some categories of covers, and then he shows that they are equivalent and so on. So he considers, you have, so what he shows is there exists y contained in x, some hypersurface. So maybe one should think of it in this setup, yeah, projective. So I mean, this is sort of more or less follows from the other, everything follows from number 2 in some sense, yeah, because yeah, somehow it works out. Okay, so one looks at so you have y, and you can complete you can look at the formal scheme, this thing which is complete x along the hypersurface y, and so this y is contained in this thing, I mean, and of course you have a map from this to x itself, yeah, from the completion, the formal neighborhood of y to x itself. So you have these chain of morphisms, and you have these categories. So covers of x, etal. So this is the category of etal covers of x, and morphisms are x morphisms, and you have category of etal covers of this guy, and you have category of etal covers of y, and you have functors in this direction. So given a etal cover of x, you pull it here, you get a etal cover of this guy, so this is that functor, and given a etal cover here, you pull back, you get. So these are functors. So what Grothendieck showed is that this is always an equivalence. So this is an equivalence of category, and he shows that this is fully faithful if dimension x is 2 and equivalence dimension x is greater or equal to, and equivalence, okay, it doesn't matter, dimension x is greater or equal to 3, yeah. So equivalence certainly implies fully faithful, yeah. So and this essentially gives you Grothendieck left sets, yeah. So I do the sort of follow the same algorithm. It's just that I have to modify proof at various places, because I have ramification somehow, and so So yeah, and in fact even these guys, yeah. So Eno and Laskinder, they also follow the same route. So they also, it's just that in their case they are only looking at tamely ramified covers. So when you look at tamely ramified covers, these are those are flat. Even at branch points, they are flat. So it turns out it helps a little bit. And tamely ramified means the extension is cyclic, so there are many nice things about it. So, but here one has to modify the argument a little bit. But I don't get the full result as such, so I can only do so much. I could only do so much. I'll write down the result.
So here, do you suppose x is smooth?
Yeah. So base, I will assume x is smooth.
Otherwise, it's weird. So.
Yeah. So sorry, projective. Yeah, so I meant in this thing. Sorry. Yeah, smooth projective.
So something is weird. So.
Yeah. No, so yeah, complex to general field is all I wanted to say. He generalized. So.
But why don't you just apply this so much into more general ones? I mean, it doesn't look like it. So when you just for hypersurfaces, it could be done.
Yeah. So I mean, inductively you can go down, right? So once you prove a hypersurface, that tells you, yeah. So you can go all the way to dimension. So if you have dimension n, you can go all the way to dimension 2 sub variety, and you'll get isomorphism. And if you want to go dimension 1, then you will only get surjective. Yeah. So there is no loss. Yeah. So I need some technical hypothesis to state some things. So maybe let xp be of smooth formal orbifold. So now I'm assuming that x is not just normal but smooth. Smooth form, irreducible, of course, and x is projective. Over the base field K, and a condition called geometric, which means that it is of the form. So P is BF, i.e. P is BF for, it's slightly weaker than this, but P is BF for some f, but not much. Yeah. So geometric means that it actually is a quotient of something. Yeah. Satisfying it. So and y. So let y contained in X be a hypersurface satisfying a technical condition. So let me not state the condition, but it's something like if I take a point in y, then somehow if I take the normalization of that local ring in the corresponding normalization of that point in these local extensions, then it shouldn't split. It should remain one point. Okay. So that seems like some Bertini kind of problem which I haven't been able to solve, so to speak. Technical condition. So under this, so maybe I'll just write under this condition, one can show that this part is an equivalence curve x at y p So there is an induced branch data on this guy, which I denote by p hat, to curve y, and you can always restrict a branch data to a subspace, at least a hypersurface of this kind you can restrict it. So this is an equivalence. Okay. So this is not this sort of yeah. So one has to do some work to get this, but.
Does this Compatibility condition have no obstruction for the dimension of x, like the Grothendieck case?
Yes, this works for dimension x greater equal to. So like in Grothendieck case, it's so everything at dimension should be at least 2, otherwise it doesn't work. So here, for instance, I forgot to write down, but this dimension x should be at least 2. Yeah.
The characteristic of the base field
It's not
no restriction.
No restriction.
Some favorable the more result for characteristic zero case.
Yeah, for characteristic 0 is already solved. So I mean, one should think of, see, the point is I'm trying to prove Grothendieck Lefschetz for which will put wildly ramified curves also in some context. Yeah. So instead of, so the problem here is, given a hypersurface, one could take some bad wildly ramified covers such that it. So what I'm trying to do is, now I restrict what wildly ramified covers of x I can whatever, some open subset of x I can take, and then if I do that restriction, then there are only finitely then there exists a hypersurface which will take care of those things. So it's I've turned the quantifiers in some ways to get things. So that is how one should put the this in right framework. Otherwise, it's not true, right? So one should try to put this in the right framework to make it work. Okay. So actually, there is a version by, but let me just. Okay, I'm really sorry for going a bit slow, but. So this is also sort of true if you assume certain things which are slightly more I mean, so if y contained in x is normal hypersurface and normal and intersects the branch locus of P transversally, and the divisor corresponding to y is ample divisor, is a very ample divisor on x, then curve xp to this curve x hat y p hat is fully faithful, and this additional one I can't get because that there somehow some sheaves are free is needed, and that relies on being flat.
Y2, where arrows seem to be reversed?
No, this is the same thing, right?
Sorry.
Yeah.
Yeah, no, sorry.
Yeah. So that this part is taken care of here, and this is there. So together under this technical condition, we have some sort of surjectivity of the fundamental group from fundamental group of curve to anything in some sense. Yeah. So okay. So my time is up, but I'll just mention one thing because this is really. So I mean, one should expect some Grothendieck Lefschetz kind of thing, because the result of KAIST Saito, who proved that. So they defined pi1 ab xt. Yeah, and so D is a Cartier divisor, and this is defined using some cohomological method. So they look at characters, so elements of H1 H. So if U is x minus support of D. Then they look at elements of H1U which has some ramification bounded by D in some sense. So they define these objects, or maybe these objects were defined earlier, but they study this and they show that pi 1 y 2. So there exists a hypersurface of X of high enough degree, and then you pull back. So maybe D restricted to Y to this. It has this property. Sorry, pi 1 ab again is surjective if dimension X is greater or equal to, and isomorphism if dimension X is greater or equal to. And it's actually a crucial step in their proof of this higher dimensional class field theory. Yeah. So one should expect something. This should be true, but yeah. So maybe slightly more work is required. So maybe I'll stop here and